Hello and welcome everybody to the fourth 2020 meeting of March. And we have here the great pleasure to present Brad Rodriguez with the MSP Threaded code force for the Texas Instrument chip. Then, Brad, you can start your presentation, please.
Okay, just let me get my screen sharing taken care of here. Your browser is preventing access. What have I done wrong? How do I do this?
Computers are evil.
Permissions, share the screen. Ah, here we are. Okay, let's try that. Select window. Press allow.
There.
Can you now see my screen?
I see it.
Excellent. Okay. Well, thank you, everyone. I'm sorry that last month's scheduling suffered a misunderstanding. Thank you all for coming out today to hear this. When Peter asked me to put together a presentation, he asked for something specifically on implementation of Forth. And I had this project sitting on the shelf collecting dust. So I thought I can finish this off and make a talk about it. So this is my presentation on token threading on the MSP 430. Now this is the target in the original impetus for the project. It's the MSP 430 G2553 chip, which that is actually a picture of the chip there. And this is used on one of the Texas Instruments launch pads. It has a 16-bit CPU, a very elegant 16-bit CPU, 512 bytes of RAM, and 16K of flash ROM, which to my mind makes it the perfect size for a fourth chip. Of the 16K of flash ROM, 8K is devoted to the Camel Forth kernel, and 8K is available for user applications. Now I have a client who uses this chip extensively and likes using Forth, and managed to, with a very ambitious application, fill that 8K of user application. In fact, I had to do a few customizations for him, moving some of his code into the kernel in order for him to squeeze it into the 16K chip, 16K of flash ROM. And I knew that this problem was going to recur, that he was sooner or later going to want to make changes or additions to his application. So I thought I need to solve this problem and make more space available for him. So the first thing that came to mind for me was to switch the threading mechanism. This word bounds defined as over plus swap implementation on the MSP 430. Each of those fourth words would compile to 4 bytes. It would be a 2-byte call instruction and a 2-byte address. So that's 12 bytes for those 3 words. Now everybody knows that the innovation of Forth, it actually wasn't innovated by Forth, but the innovation used in Forth is the address threading, where we get rid of the call instructions. We just put the address of the subroutines, and then we have an inner interpreter which traverses that, executing them one at a time. So that gets us from 12 bytes down to 6 bytes on the MSP 430. But we were already using that, so I had to make it smaller. The next step is the idea of token threading, where instead of using the address of each word, you have a smaller token that represents each word. So you have a token for over, a token for plus, and a token for swap, and typically these would be 8-bit tokens. Now that gets us down to from 6 bytes for that to 3 bytes for that particular phrase. And what we need now is a mechanism to get from the token, an 8-bit token, to the actual address of the code to execute. So somewhere in the memory of the system, there will be a table of the addresses for all the various tokens. So there'll be an address of plus, address of drop, address of dupe. And each token is then an index into that table. That can be done very quickly, very efficiently. The problem now, from a purist standpoint, is that Forth is an extensible language. You can add words. You can add thousands of words if you have enough memory space. And how does the token mechanism handle that? Well, there are basically two approaches. If you're a purist, you decide that every fourth word must have a token, which means that you have to have an extensible token table. You can't just have a fixed size token table because you don't know how many words the end user is going to add. And you have to have some way to encode those tokens. 8 bits isn't going to do it if you have thousands of words. So you either have to enlarge the encoding or you have to get to something creative in data compression, like a mixture of 8-bit and 16-bit tokens. But 16-bit tokens aren't a lot of help in the MSP 430 where the address is 16 bits. So the second approach is what I call the hybrid approach, where a selected subset of the words, a selected subset of the vocabulary is tokenized, has tokens, and the rest do not. So this gives you the advantage that you can have a fixed size token table, and you can have a fixed size token. You can have an 8-bit token with 256 entries in the token table. This does, however, require you to have some mechanism to reference or to call the other words that are not tokenized. You put a token in the thread and the token table, the inner interpreter will look up that token and execute it, but what do you do if there is no token? So for this, again, there are two options. There's probably more than two options, but these are the two that came to my mind. The first is to have some kind of a call token. You may call one of the 256 primitives of this machine, and a call byte is followed by 2 bytes of address, low and high, or high and low, depending on your architecture. The problem with that is we've now taken a 16-bit address thread, the 16-bit address, which we had in our address threaded system, and we've changed it to a 3-byte construct. It has to have an 8-bit call, then the 16-bit address. The other approach, and what I chose, is to use special encoding of the token and the address. I am taking advantage of the fact that, first of all, the MSP 430 requires all routines, all addresses of threads and machine instructions to be even aligned. It has to be on a word boundary, which means the least significant bit of the address is going to be always 0. So I use the least significant bit 1 as a flag that, no, this is not an address, this is a token, and that gives me 7 bits remaining for the token. So I have 128 possible tokens. If the least significant bit of the address is 0, then it's a 2-byte address, and it's a 2-byte aligned address. And this works because, number one, I mentioned the addresses for instructions have to be aligned, and number two, because the MSP 430 stores addresses and 16-bit values, low byte and then high byte. So we're going to fetch the low byte first. Last month, Julian Skidmore talked about the Fignition, and he had a totally different, he had this scheme, but in a totally different implementation. Instead of using a bit flag, he was using a range of values, excuse me. Below a certain value, byte value, it was a token, and above a certain byte value, I think it was 40 hex, but I'm trying to remember. Above that certain byte value, it's an address, a 16-bit address. It all depends upon your particular hardware, what your processor architecture is capable of, and excuse me, and how addresses and how data is stored in memory. So, given this, what does next begin to look like? On the left, we have the classic indirect threaded code next used in CamelForth. It's 2 instructions, and being 2 instructions, it's usually just compiled in line with a macro. So it's move using the instruction pointer, indirect post increment to W, and then move from the indirect post increment from W into the program counter. That's loads an address into the program counter. Actually, it loads the code field of a word into the program counter. In the token threaded example, we have to look at a byte. We move the first byte into the W register, and then we look at that least significant bit. If it is 1, it's a token. If it is not 1, if it is 0, it's an address. So then we fetch the second byte of the address, merge the 2 bytes together into a 16-bit value, and use that, fetch that as the code field of the instruction. And we have to do it this way because 16-bit moves on the MSP430 must be aligned. And once you allow byte tokens in the instruction thread, in the compiled thread, you're allowing the possibility of unaligned addresses. So we have to do 2 byte fetches, which can be from any address, and then we merge that together to make a 16-bit value. So we're basically synthesizing an unaligned 16-bit fetch on a machine that requires alignment for the usual 16-bit fetch. And then finally, if it's a token, we just use that as an index into the token table. A -1, of course, is to get rid of that set least significant bit. We fetch from the token table into the W register, and then we fetch the code field of that word into the program counter. So you can see that it's slower, but not terribly slower. It's actually a fairly efficient. We replace 2 instructions with either 5 instructions if it's a token, or 7 instructions if it's not a token. Excuse me. So with all that, what is this magical token table? This is, and I apologize for the complexity of the slide, this is the token table currently used in the MSP430. What is interesting about this is the first 10 rows of the token table. Well, there are some constants in the first row, but other than the constants in the first row, the first 10 rows in the token table correspond to the code primitives of the MSP430 Camelforth. There are about 80 less 7, I think it is, 80 less 6 code primitives that are implemented in machine language under Camelforth. Everything else is done in high-level code. So those are the obvious candidates to be put in the token table. That left me with some room in the token table for more tokens. And the next 5 rows I just took out of the high-level core. These are words which I think are commonly used. So, and this is a judgment call on my part. These are the words that I thought would be most likely to be encountered frequently and therefore give the most savings if converted from 16 bits to 8 bits. To do this properly, I should have taken my client's application and done a frequency count on the words that he uses, but then that would have been just one application. I would have probably wanted to look at several applications and do a frequency count on the words that are most commonly used, and those are the ones that get moved into the token table. I have 5 currently unused tokens that are for future development. So if anybody wants me to come back to this later, I will, but it's a lot to digest. Now, given that we want to be able to compile an 8-bit token for a word, and the compiler, of course, is running on the MSP430, where does the compiler find that? I am saved here by an extravagance in my past. When I first did the Camelforth model, I set aside a byte for the immediate flag, which is extravagant because the immediate flag is 1 bit. So in the header layout of the Camelforth for the MSP430, there is, of course, the link field. It's stored as a singly linked list. There is a byte holding the immediate flag, a name, and then the body of the word, which is the code pointer because it's indirect threaded code, and a thread if it's a high-level definition. So I have those 7 bits available in the unused in the immediate flag byte. And what did I just decide? But I'm going to have a 7-bit token, so it fits in there perfectly. So this did not, in fact, enlarge the header. If you didn't store your immediate flag that way, you might have to add a byte. So the compiler, when it looks up a word, knows immediately, pardon the pun, knows directly that a word has a token representation. And if the token is all ones, so if the immediate flag byte is either all ones or all ones with a 0 least significant bit, then it knows it does not have a token. So FF is the unused token. It indicates to the compiler that it has to compile an address instead of a token. So on the MSP 430 indirect threaded code, the words are all address aligned. In particular, the code pointer is address aligned, and the thread remains address aligned. So the start of every new word is even address aligned. Sorry, I should say word aligned. Oops, went there too quickly. No, I didn't. Given that a word can be referenced in a thread, can appear in a thread either as a token or as a code field address, it raises the question from the standards viewpoint of what should the execution token be. You see the XT several times in the standard, and after thinking about this for a while, I decided that the XT should be smart. On this system, if an XT value on the stack, if it is odd, it is an 8-bit token. If the least significant bit is 1, it is an 8-bit token. If the least significant bit is 0, it references a code field address. The execution token is a code field address. This affects words that produce or return execution tokens, words like find and tick and bracket tick, so they can return one of these complex values. And it affects words that consume the execution token, like execute, compile, comma, and to body. Those are all words that in the standard take an execution token and do something else, do something with it or turn it to something else. So if you tick dupe on this system, you will get a hex 13, always, regardless of the address map, because 13 is the token value assigned to the dupe instruction. I'll just jump back to, if you can look on the second row of the table, dupe is 13 hexadecimal. So this unfortunately breaks some habits. I'm so used to being able to do something like tick word name 20 dump to look at the code of a word, and if I try that with dupe, it doesn't work. There is another word called XT to CFA, which will, given an execution token, look up the code field address if necessary. So I think this is the correct implementation of XT for standards compliance on this system. This is I've never seen anybody else's token threaded system, so I don't know what other people are doing in this regard, but this seems to make sense to me. I put in a few other optimizations. Remember, the whole objective here was to make the compiled code for the application smaller. First, I put in short literals, which instead of a lit, it has a C lit in the range of -128 to 127. So we have a byte token and a byte literal value. And that actually handles all the literals in the kernel except for, I believe, 3. There are 3 literal addresses stored in the kernel, but all the other constant values are either using one of the named constants like 0, 1, and 2, or short literal values. I also have begun implementing short branch offsets. So the standard branch and question branch primitives take a 16-bit offset. And I'm starting to implement short branch and short question branch, which take an 8-bit offset. The problem with doing that, I could have done that for all branches automatically, but I've discovered in the past that as soon as I limit the branch range to -128 to +127, there's going to be a piece of application code that requires a branch offset of, plus or minus 130 or something like that. So right now I'm only doing branch and question branch. It turns out the do and loop are only used, I believe, 4 places in the CamelForth kernel, and I'm not yet to the point of optimizing for the application. So token threading, short literal, short branch offsets got me some space. The magic question is, what's the result of all this? On the original indirect threaded code, CamelForth, the kernel, the actual CamelForth system is about 7.2K, less than 7.5K is how I like to think of it. And my favorite test, which is do I drop loop, which I can do 10,000 times and measure it with the on-chip timer. Do I drop loop for one iteration takes 3.88 microseconds. With the token threaded code, the kernel is now 6,580 bytes, which is just under 6.5 kilobytes. And the do I drop loop takes 7.5 microseconds. And I have done several different tests for speed with nothing inside it and do loops with something more complex inside it. And it's always pretty close to this 2-to-1 ratio. So the token threaded code runs at half the speed. It takes twice the time. Runs at half the speed of the indirect threaded code. And the project I had in mind for this wasn't speed sensitive at all. A lot of applications can run slower and don't require maximum performance on the part of the processor. So that's an acceptable trade-off. I confess to some disappointment that I was really hoping to get it down below 6 kilobytes, and I don't seem to be able to do that. But 6.5 is good because on this chip, the flash memory is allocated and erased in half K blocks. So instead of allocating 8K for the Camel4th kernel, I can allocate 6.5K and then leave 9.5K available for the application. And the application can then erase the areas. It can be erased without affecting the kernel. So very happy to get it below 6.5K because above 6.5K, I would have had to allocate 7K. Now, that's where it stands as of today, but it turns out there's one more improvement that could be made. We have replaced addresses in the thread, many of the addresses in the thread, with tokens, 8-bit token instead of a 16-bit address. What about that code field? The code field is an interesting target for optimization because unlike the thread, where we can have an infinite number of fourth words or limited only by memory, there's only a small number of actions that the code field ever takes. It typically does do colon, do var for variables, do con for constants, do code for machine language definitions, which is usually just a pointer to the code that follows. And so why not do with that what we did with the 128 fourth words, replace each of those with a token and then have a lookup table. That's where I'm going next with this. So I have to solve the problem of how to implement create and does correctly. But this should then save 1 byte for each fourth word. And in the Camel4th MSP 430 kernel, there are 260 fourth words. So that would not get me another half a K, I'm sorry to say, but I maybe could shove a few more functions into the kernel. This, by the way, makes me realize that we've been naming our threading models all wrong. When we refer to indirect threaded code, what we're really referring to is that the code field, or what I'm starting to call the action of the word, is indirect. It's the rather than the code field being where machine code is stored, the code field is, sorry, what was I starting to say there? Rather than the code field being where the machine code is stored, the code field is the address of the machine code. So, and it's not really indirect threaded, or rather it's always indirect threaded. I prefer to think of it as address thread. So what we've been calling an indirect threaded code, I am now starting to call indirect action address threaded. Address thread distinguishing it between having subroutine calls and having just a list of addresses. So what we would call direct threaded code, I am now starting to call direct action address threaded. What I have just implemented and talked about is indirect action token thread, and where I am going is a token action and a token thread. So there's actually 2 different design decisions in the threading model, and I'm starting to develop the terminology to handle that. Having said all that, that's where I stand now. Are there any questions? Should I leave this? I'll leave this up for a bit in case somebody wants me to go back to a previous slide.
Thank
So
you very much.
you mentioned that create does might be a challenge. Can you go into that a little bit deeper?
Yeah, let me back up. I said that there's a limited number of actions that are required in the code field, and the exception, of course, is create does, where you can have user-defined actions in the code field. And how to implement that is the question. We want to be able to provide an address for the code field to a user-defined routine. One way would be the old Fig model. We have a do does action followed by an address. Another way, and that would be pretty straightforward, because we just make do does one of the tokens. The F83 model was that every does clause in a user-defined defining word. The does clause point is actually a fragment of machine code, and we store the address of that machine code in the code field address of a defined word.
Right,
What
short interruption.
I would think of doing in that case is the exact same thing I've done for the threading model, which is I would store, if it's an even address, then the code field is pointing to code. It's pointing to the code that implements the does clause. And if it's an odd value, then it's a single byte token that is referring to one of the standard does actions like do colon, do var, do con, or do co. So that going, I just haven't implemented it yet. Does that answer your question?
Mm-hmm. I think so. You were quite distorted, and maybe you switch off your video.
Does that help?
To save bandwidth. Yeah, sounds like it helps a lot.
Are there any other questions?
Ah, okay. Yeah, now the sound is much better.
Go ahead.
Dimitri.
The audio? I'll try the chat.
I'm sorry if this was answered in the last question. I left the.
Can you hear me now, dear?
Yeah,
Yes.
you're nice and clear.
Now that's weird. I shut off for a while. How much of my answer got? Do I need to repeat the answer from the last question?
That would be
Yeah,
great.
you really do.
Okay, sorry. The problem with does, when you have a word with a does clause, the user is providing an action for a newly defined word. So if you want to create your own version of, if you want to define an array, for example, you're going to provide the action for the array. In the Fig model, the old Fig forth model, there is a specific action which is, for lack of a better phrase, I'll call it do does, which goes into the code field, and it is followed immediately by the address of a thread. And that was efficient and elegant. I can stop sharing my screen. Hang on a second. No, that was the wrong.
Oh, we can hear you fine while you're sharing.
Yeah, I'll leave the screen share for the moment. Peter had asked me to stop sharing the screen. Anyway, the Fig model was, there was one particular routine, action routine called do does, which was then followed by the address of a thread, which was extravagant in memory usage compared to what was desired. In the F83 model, each does clause was actually converted into a fragment of machine code. There's a little bit of machine code that gets compiled in to the parent word. And then the child words, all the defined words, have their actions pointing to that. Now, I've decided there's two ways to implement this, basically corresponding to the same two ways I was handling the thread. I could create a single byte token, which is do does, and followed by a thread address. And then the thread address is in the defining word, and all the children of the defining word have those 3 bytes, a 1 byte token and a 2 byte address. Or I could use the same encoding technique that I used for the tokens in the thread. I could say if the least significant bit is 1, then the action, the code field, contains a token and needs to be looked up in the lookup table. If the least significant bit of the code field is 0, it is then an address and can be called as machine code, just as it would be in the F83 model. So I haven't decided which of those I like better yet.
Thank you very much.
And I'm still trying to figure out how to unshare my screen.
I have another solution for the create DOS problem. I consider the data field of the create DOS word consisting of 2 fields, the data field, in the ISO sense, and a pointer, and that is very clean, and it costs a lot of 64-bit pointers, and I don't care because I can enhance the dictionary space beyond 128 gigabytes. And that is a whole different stuff of the MSP 430, I think. But it is very clean, very clean.
Okay, thank you. I'll have to come back and do a follow-up presentation when I get this resolved to my satisfaction.
Mm-hmm. So Ben raised his hand.
I think Dimitri was first.
Yeah, I have actually a really kind of a fundamental question, which is, what is the difference between an XT and a CFA? I don't really understand.
This is probably the best example of there being a difference. And tremendous number of Forth systems, there is no difference. The XT, the execution token, is the code field address. The execution token is, and forgive me, I don't have the standard definition in front of me, so if I'm misquoting the standard, someone please correct me. The execution token is the value that specifies how to execute a particular Forth word. It identifies a particular word and how it is executed. Normally, that's an address. When you have a token threaded system, when you're starting to use tokens to represent Forth words instead of addresses to represent Forth words, then the XT can be either a token or an address. In a pure token threaded system where every single fourth word was assigned a token, then that token would be the XT. And you'd always have to do some kind of a translation to convert that to an address of executable code.
I see. So in the purely token threaded system, the XT needs to be turned into a CFA to find the code that needs to be executed.
Correct.
Right. Okay, that makes sense. But that's not how many fourth systems work. So that's why it becomes confusing. Okay, that makes more sense.
Yeah, I think I don't know of that many token threaded systems, and I'm not that conversant with a large number of fourths. But I think overwhelmingly, the majority of fourths use the code field address as the execution token.
Mm-hmm.
But it was actually very, very good forethought on the part of the committee to come up with this idea of an execution token rather than an execution address, because it makes systems like this possible.
Mm-hmm.
Okay, that makes sense. I may ask just one more question, which is, I noticed when you shared the token table that there were constants in that table. Why are they there? What are they used for?
Some fourth systems define constants as certain key constants as fourth words. For example, there will be a fourth word with the name 0, the digit 0. The reason being, two reasons actually. On some systems that's faster. It's faster to do a machine instruction that pushes a 0 than to do all the work of DoCon. And on some systems it's smaller. For example, if you take the MSP 430 indirect threaded code and you compile a 0 into a word, you'll get the address of word literal, actually lit is the runtime, and the value 0. So a literal 0 on the MSP 430, the original MSP 430 would compile as 4 bytes, lit followed by the constant 0. If you make 0 a fourth word, then every time you use 0 on the original MSP 430, it becomes 2 bytes, just the address of a word. And if you then tokenize that, it becomes 1 byte. So every place I use the value 0 is compiled to 1 byte.
I see. So it's not the value 0 that's being stored in a token table. It's a token for a word that does that.
Exactly. It's a word that actually has the name 0.
Right.
Yes.
Okay. The name of it's 0. Okay. Thanks. That clears it up for me.
That was always one of the fun things about explaining forth to a newcomer, is that you could actually name a word. And if you wanted to be a prankster, you'd define a word 0, which returned the value 1. So every time they tried typing 0, they would get a 1 instead, because the word name takes precedence over the numeric value. Hope that answered the question.
Yes,
More
great, thank you.
questions? Who is
Ben.
next? Ulrich?
Ben. Ben
Okay,
is next.
yeah. So yeah, I appreciate the slight indulgence. Just it's really awesome, Brad, to finally see you speaking and stuff, because I think your Moving Forth series, which I think I originally read in the 80s, was it Microcornucopia magazine? It was one of those hacker mags.
It was in the Computer Journal.
Computer,
Mhm.
yeah, okay,
TCJ.
Computer Journal,
Mhm.
yeah. So that really, I mean, I was excited about Forth and was trying to figure out how to do my own Forth on my own systems, and the threading model explanations just completely opened my mind to what was possible. And I actually built a tiny Forth-like environment on a Hero 1 robot, which had something like a 6809 on it. And your article also, convinced me that the 6809 was like the best ISA for 8-bit processor of all time. So anyway, it's really cool. Finally hearing from you. I'm just wondering if you're able to reveal what the nature of the application is that your client has, if you can disclose that, and what the performance and energy requirements are on it.
Unfortunately, no. Sorry, I can't.
Well, if you can't say functionally, what kind of energy and performance requirements are you needing to get out of this? Because you've gotten you saved like 9.5% code size, but you almost doubled the execution time on it.
Let me think of what I can say about this application. This is a telemetry receiver works with a companion unit, which is a wireless transmitter. And it has to receive data once per second and display that on an LCD. The data is only sent once per second. So it's sitting in a loop, waiting for data to be received, and then it receives that, does some formatting and maybe a little bit of processing, like it keeps a maximum and minimum value, for example, and then puts that up on the LCD, which is not a very demanding task. You don't need an ARM chip for that. So there's never been a problem with the unit running out of processing power. We've had lots and lots of speed, even with a little 8 megahertz MSP 430. But there's always that trade-off, and that's, you know, if you have a speed intensive, a CPU intensive application, you either don't do this trick, this technique, or you use a faster processor.
That processor versus like the 6809, like it supports like 2 stacks or something. It's like, how do you compare it against other 8 bits?
Well, actually, it's a 60-bit processor,
16-bit,
and
yeah.
It's marvelous. It supports 16 stacks, actually. Well,
Oh,
no,
wow.
I have to take. If you're familiar with the PDP-11, this is probably as close to the PDP-11 as you'll get in a modern microcontroller. It has 16 registers, and any of them can be an address register with post increment and pre-decrement. And the only gotcha is that of those 16 registers, 4 of them are pre-dedicated. One's the program counter, one's the stack pointer. Again, the program counter is a general purpose register, just like in the PDP-11. And they have one register which they call the constant generator, which when you read that register, you always get a constant value depending on what addressing mode you use. Very elegant solution to the problem of getting constants quickly.
Very cool. Thanks.
It's a ferociously elegant processor. I was able to describe it in 2 pages.
I'll have to check it out.
Yeah, very nice.
Brad, I have a question, if I may.
Yeah, maybe
Certainly.
I'm first, but yeah, you go ahead.
I'm familiar with the MSP 430. I know you've touched this in your previous response, but did you find the 16-bit architecture, the ISA, a good fit to the 4th virtual machine?
Interesting question. Yes, I think that the instruction set architecture of the MSP 430 is very good fit to the 4th virtual machine. If you go to a direct threaded code, conventional direct threaded code implementation, next becomes one machine instruction.
Yeah.
So it's very powerful with its addressing modes. And the indirect threaded model that I chose to use next is 2 machine instructions. And it has no problem implementing multiple stacks because, as I just said, all the 12 really available registers can be used as stack pointers and can be used for auto increment and pre-decrement addressing.
Okay, thanks. It's just a shame that there's unlikely to be any further development into the MSP 430 core. We're not going to see a multi-hundred megahertz version of it anytime soon.
Yeah. But maybe we would see some more application because of the chip crisis. Texas Instruments is one of the few companies that can actually deliver chips. So I have a question and a remark, or more, remark and a question. The remark is that's the company Servonaut of Jörg Völker, and he uses STM8 with a very similar architecture from the 4 system that you have to conserve space and a hybrid token and a direct threaded model. And Jörg has this issue that STM8 chips are no longer available in the short term. And so he's actually considering to move to MSP 430, which means he would be very interested in probably learn about your threading technique, so he can build up on that. So that would be really great.